If two blocks connected through a spring are pulled apart, the force with which they are pulled towards each other increases with the increase in separation. But what about electric charges? Does the force between them increase or decrease with the distance? Does it depend on the distance at all? Let's find out. Take two balloons and rub them gently with fur. Now suspend them so that they are near to each other. You will find that they repel each other slightly. If you now bring fur near the balloon, you will find them attracting each other. We note that the static charges have developed on these balloons and the fur. These charges are responsible for the attraction and the repulsion effects. Now rub both the balloons vigorously with fur to impart more static charges on them. You will now find that the repulsion between them has increased. That is, more the charge on the balloons, greater is the force of repulsion. On increasing the distance between the balloons, you will see a decrease in the repulsive force. The force of attraction or repulsion between two electric charges at rest was studied by Charles Coulomb in the 18th century. He formulated a law which states that the magnitude of the force of attraction or repulsion between 2-point charges at rest is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. Let Q1 and Q2 be two positive point charges at rest separated by a distance r. The magnitude of the force of repulsion F is proportional to Q1 times Q2 and inversely proportional to r square. Combining these two equations, F is proportional to Q1 times Q2 divided by r square. So F is equal to constant K times Q1 times Q2 divided by r square. Here K is the constant of proportionality. When the charges are placed in a vacuum or in free space, K is equal to 1 upon 4 pi epsilon 0, where epsilon 0 is the electrical permittivity of vacuum or the permittivity of free space. In the SI unit, its value equals 8.85 times 10 to the power minus 12 and has the unit Coulomb square per Newton meter square. Force, being a vector quantity, has both magnitude and direction. To understand the vector nature of the Coulomb force, let's express Coulomb's law in vector form. Let vector F21 represent the force exerted by Q1 on Q2 and R_21 be the unit vector along the line joining the two charges from Q1 to Q2. Hence, it acts along the line joining Q1 to Q2 away from Q1. Let vector F12 be the force exerted by Q2 on Q1 and R_12 be the unit vector along the line joining the two charges from Q2 to Q1. This force acts along the line joining Q2 to Q1 away from Q2. Since unit vectors R_12 and R_21 are in the opposite directions, R_21 is equal to minus R_12. Therefore, the forces are opposite in direction and equal in magnitude. Similarly, the 2-point charges of the opposite polarity will exert equal and opposite forces on each other. The two forces form an action and reaction pair. Since the two forces act along the line joining the two charges, the electrostatic force is called a central force. You must note that Coulomb's law is applicable only for point charges at rest. But what if charges are placed in a medium other than a vacuum? The force between the two charges when placed in a medium is expressed by a variation to Coulomb's law seen in the equation. Here, epsilon is called the absolute permittivity of the medium and can be determined experimentally. To summarize, static electric force can be either attractive or repulsive. The magnitude and direction of the electrical forces can be given by Coulomb's law. Two forces acting between the charges form an action and reaction pair. Electrostatic force is a central force. We talked about the vector form of Coulomb's law in brief. Stay tuned for a